AI agents have evolved from basic editor autocomplete suggestions to autonomous operators capable of generating code across multiple files and directories. These agents are now opening pull requests, proposing structural changes to infrastructure, and executing complex engineering tasks with minimal human intervention. This creates an immediate conflict with traditional DevOps. Legacy pipelines were architected for a world where every change happened at a human pace. Engineering teams often see an initial surge in traditional productivity metrics, lines of code increase, and the frequency of merged pull requests climbs. However, this volume often conceals a surge in undetected regressions, hallucinated logic, and configuration drift that reaches production environments. The core issue is that current pipelines act as gates for human authors, relying on the assumption that the contributor has a complete understanding of the business context and technical trade-offs. When this human trust model is applied to code generated at machine speed, the existing trust boundaries completely collapse. Volume-based metrics are no longer reliable indicators of success. They often mask an underlying inflation of technical debt. This transition highlights a specific engineering reality. AI agents act as force multipliers for whatever system they operate within, whether that system is healthy or broken. Deploying an agent into a fragile CI/CD environment with manual steps simply causes the system to fail more frequently and at a higher velocity. If a repository has thin or trivial test coverage, the agent will produce and ship untested code at a rate that human reviewers cannot manually validate. Infrastructure changes proposed by agents in environments without strict drift detection can lead to rapid, unmonitored inconsistencies across production clusters. Reliability practices that were important for human developers become mandatory when code is being generated at machine scale. To maintain stability, engineering teams must rebuild the repository as a machine-readable interface and transition the CI/CD pipeline into a system of active verification. In this environment, the CI/CD pipeline becomes the primary engineered safeguard for maintaining software integrity. Before scaling agent adoption, teams must audit their DevOps foundations against a set of strict engineering prerequisites. The first requirement is a fully automated build, test, and deployment process. Without a reliable feedback loop, agents produce code that passes locally but fails in production. The second threshold requires comprehensive tests to run on every pull request with strict coverage. Third, all environments must be provisioned through version-controlled templates with active drift detection to prevent manual configuration errors. While a human infrastructure mistake can be caught and rolled back, an agent can replicate an architectural error across an entire system in seconds. Strong branch protection rules and comprehensive production observability provide the final necessary safety nets. These foundational elements create a containment area that allows for safe experimentation with agentic workflows. A frequent failure in AI adoption stems from a reliance on tribal knowledge. The implicit conventions means treating the repository as an interface, where architecture documentation serves as an operational input rather than just a reference file. Skill profiles and instruction files, like github/copilotinstructions.md, establish the architectural boundaries and dependency policies the agent must follow. This marks a shift away from traditional prompt engineering, which is often ephemeral and ad hoc. In specification-driven development, engineers write versioned, structured criteria that define the absolute requirements for a successful contribution. These specifications serve as durable documentation, reducing the need to maintain separate, disconnected user stories or design docs. A precise specification provides an agent with the same technical and business context that a senior engineer needs to execute a task correctly. Traditional CI/CD pipelines function as simple gates, checking code against a static list of requirements. They verify basic criteria, whether the code compiles, passes its tests, and meets formatting standards. When an agent produces the code, the implicit human oversight that usually accompanies these checks is no longer present. The pipeline must be capable of detecting if an agent has generated trivial, self-validating tests specifically designed to bypass the beld. This requires active verification across 3 mandatory layers. Layer 1, structural verification, enforces file placement and dependency policies. Layer 2, semantic verification, validates the implementation against the specification's acceptance criteria. Layer 3, provenance verification, traces artifacts to legitimate sources to mitigate AI-driven threat factors. This layer is designed to catch hallucinated dependencies, typo-squatted packages, and autonomous supply chain poisoning. This 3-layer system ensures every contribution is architecturally sound, semantically correct, and cryptographically verified before it reaches production. Because an agent can produce thousands of lines of code in a single session, volume metrics like commits per day have become misleading. Engineering leaders are moving toward trust boundary metrics to measure true effectiveness. These metrics track the precise ratio of agent-introduced defects caught by the pipeline versus those that successfully reach production environments. This shift in measurement fundamentally changes the daily responsibilities of the software engineer. The role is evolving into a system designer, an agent operator, and a quality steward. Engineers now focus on creating the architectural scaffolding, policy as code, and strict governance frameworks that allow autonomous agents to contribute effectively. Most teams currently operate at a foundation level, but the goal is to reach an optimized end state where agents are fully integrated into the lifecycle. This includes the move toward pipeline as specification, where verification depth adjusts automatically based on the risk profile of the code being submitted. The objective is continuous compliance verification, a system that maintains the integrity of the repository in real time. This enables a collaborative remediation loop. The pipeline identifies an issue, feeds the failure back to the agent, and allows the agent to auto-remediate. In this model, human intervention is only required when the agent cannot resolve a conflict within its approved operational scope. The future of software delivery is built on these rigid, accountable structures, allowing humans and machines to collaborate at machine speed.